hopefully you'll be more interested in general in good data science practices. So I'd like to tell you a few things about that. First, I'd like to show you the cases we've took part in. So what we do at DeepSense.io, we develop data science solution. In particular, we're very focused on deep learning. So what we did, we developed algorithms, one for predicting the species and particular specimen of a whale. So there was a problem, like you had a rare species, endangered species of a right whale, and you had to, scientists wanted to keep track of the whales. And we developed a solution which was able to recognize from a picture which whale is it. Okay, and we took first place at Kaggle competition, like a big margin. And the second competition we took part into, it was a recent competition on Kaggle satellites. About satellites, the problem was to perform a segmentation on images. So you have a satellite image, and the point was to say where's water or a road or whatever, just color it. Okay, it's a very common problem, segmentation problem. And we got fourth place. And today, I'd like to tell you a few things, like how to train the model, how to review a history of a model, how to have a proper teamwork. So like you're not sitting in your basement coding alone, but the proper teamwork is important. Next thing, how to reproduce the model. So when you finally get to the solution, the important case is to be able to reproduce it. And last thing, like in the end of the pipeline, when all the data scientists sat and they coded, they developed some solution, there was obviously a lot of experimentation. You reproduce the model finally, but what then? Someone has to be able to use it, so you deploy the model in the cloud with some API and so on. Okay. So these are lessons learned the hard way. Well, I'm supposed to mention that we had these problems. We tried to solve them. That's what I like to tell you, share the knowledge. So the case I'd like to show you, it's an exemplary job, the project I prepared for you. It was recognition of animals. So you have pictures of bears or bisons. I think I missed the elk, actually. Well, I liked it, so there's a picture. And the problem is to recognize whether on the picture, what's the animal in the picture. Okay? So we're wondering. We see a picture, and is it the bear or the bison? It was an iNatural's data set. I think it's by Google. It's a large data set, many animals. So I took a subset of the data set and prepared it for you. So it's deep model based in the sense that, OK, we are generally very focused on deep learning because the recent solutions are really state-of-the-art solutions, definitely in the vision, but also in time series analysis. Everywhere where you see some structure, deep learning really shines. And that's the solutions we apply. But it's really on the cut edge of the technology. In the sense we read a lot of papers. We try to reproduce a solution which initially was developed by scientists. Maybe there are some scientists here. No, that's very good, because it's often very messy. You know, to reproduce a solution which was developed during the experimentation phase is something really difficult. Definitely from a paper when you don't have the source code. Yeah. So why did I mention that? Because that's deep learning. That's somehow difficult. And the model is based on ResNet architecture, so it's just a neural network, recent from last year, I guess, which is somehow specialized in this sort of problems. Okay, so that's a problem. Okay, the technologies we've used, so it's pretty standard in the sense it's some version control, some library for deep learning, Docker to keep track of the environment you run the experiment in, and Neptune, our in-house solution for the problems in these other areas I'd like to also mention. Okay, then there's an example of model training. So you've got your model working, you have some code, and you want to keep track of what's going on. So you may use some spreadsheets You may use some logs. We've all done it, I guess, and it doesn't scale in the sense that keeping track of everything in some spreadsheets or logs. Okay, of course, you can just process it, put it into some, I don't know, Python notebook, try to find the proper rows or whatever, but it really doesn't scale well on the whole team, on, like I said, some other issues like reproducibility and so on. So you can keep track of it, but it doesn't work. It's a bad practice, I would say. And what's a good practice? The good practice is using some logs which are transferred to the whole team, probably. Some graphs where you can visually assess the information, any information. I know it's very vague. We'll come into detail soon. And probably some images if you work with images, maybe some sounds if you work with sounds or whatever. Probably all the time when we work with some data, at some point you want to hear it, feel it, see it, whatever. Okay? And I'd like to show you an example of tracking of an experiment. So here we have a list of experiments, but I've prepared these experiments for you, but that's a whole list of different experiments. There are actually two kinds of experiments. And one is some experiments are tagged by Alice. Alice is a good data scientist. And some are tagged as Bob. And Bob is somehow not on the level of Alice, actually. And yeah. And first, maybe I'll show you some, say, pretty normal standard Alice's job tagged the good, okay? And how it really looks. So Alice keeps track of all the data. Actually, Bob also does, but he's not that advanced as Alice is. So definitely everybody plots some charts to visualize the data. So we send some metrics. And in this particular job where we try to recognize this animal, right? Is it a bear? Is it a moose or whatever? So we'd like to, one of the metric is error on the batch. So while the experiment was performed, there was sent some data, and the error was computed on the data in the sense that it was simply the number of not correctly classified images. Okay, so it's the opposite of accuracy. It's 1 minus accuracy is the error. Accuracy is accuracy, so how much were accurately classified, and classification loss, and so on, so on, so on. Okay. The other, okay, maybe two somehow non-standard things are, I've plotted also time of iterations, and since when you have the deep learning experiment, it's somehow important to keep track of the time, in the sense that some deep learning experiments, they really take even 3 days or longer. Recently in one paper, guys performed experiments which took them 3 months, I guess. Well, one experiment, simply this continuous experiment, which was, which simply took 3 months on the GPU, so it was really hardware intensive, and it still took a lot of time. The data sets are large, the images are multi-dimensional, and it takes time. So I've plotted time of one iteration, and from this data, you may, for example, read that generating of data takes definitely too much. You can put it in some multi-processing or whatever. Okay, you have to plot it first. And there's learning rate. It's some strange curve, so just to keep track of it. Here you also have channels. So the data is sent also to the channels if you want to precise mathematical information about the data, but let's leave it for now. I highly encourage to plot everything, since, come on, who prefers that and trying to analyze all these numbers than just assessing visually whether it goes up or down? Really, don't do this. But somehow non-standard and more interesting is keeping track of what's going on your data. So online during the training, I'm sending the images of these animals and probabilities, what the, say, network thinks, output of the network. Okay, so it's interpreted as probability. So network thinks that we have bison over there, that there's a bear, and so on, so on. You can enlarge it, actually. That's a bison with 0.8 probability. It's fine. That's a bison. Our network's doing great. I've also sent some logs. And during our experiment, I also keep track of the parameters. So when you perform a data science experiment, you need to keep track of the parameter. What I mean by a parameter. Usually it's something that doesn't change during the execution of the job. So at first, when you run the job, you define some not mutable parameters that somehow define your job. Okay, so when you want to reproduce it, you simply know what was the parameters. In particular, I've added the paths to the data used. Okay, when you simply change something, you have the information whether it was changed or not. Oh, there's an additional tab. It's called Actions. It's used to interact with your training. So in the job, in the Python code, I simply defined a function that when I simply use this front-end run button, it will execute, for example, saving model in a separate process. It's OK? Does everybody understand that? OK, simply in a separate process, I can somehow interact with my training. Since it's a deep learning job, when it takes some time, it's not always convenient to, I don't know, stop the training and rerun it. Often you'd like to interact with it through, say, predefined set of actions. So that's what we can do. Okay, so that's a model job we'd use. But these particular jobs will be simply easy and convenient way to show you some other practices I'd like to show you. Yeah, so interact with your training. Like I said, we have predefined actions. So best practice is to restart the job from scratch. So every time you see some, say, possibility for exploration with changing the, OK, most standard would be changing the learning rate. It's a real use case. I'm not saying like it's out of the blue, really. In the Wales, the Kaggle competition, which we won actually, we kicked the learning rate, which is somehow non-standard. I tried to read through some papers, but I haven't found anything similar. There was, like, I guess one where they performed something similar, but not precisely the same. It was like when the learning rate has some value, it may be like small value at the very beginning, and then you change it for a larger value. So your model learns, and then you change its learning rate for a higher value. It may happen when the training is unstable, and if you initially would start with high learning rate, the model, the weights of the network would not converge. Then you start from a smaller weight, from a smaller learning rate, but at some point, when the training somehow stabilizes, you'd like to kick the learning rate from for a higher value, simply to give them all some momentum. Okay. So, yeah, I've already showed it, but I'd like to show you the particular case of the kick learning rate. So I've prepared this particular experiment where at some point in time I just performed an action of kicking the learning rate. So I've changed it arbitrarily to 0.01. In parameters, we can see that at the very beginning it was much smaller. And actually, residual network, this ResNet 50 network, this deep network is quite big, and it doesn't respond well for such changes, in the sense that if each parameter of the network is updated with this bigger learning rate, it becomes completely unstable, and we see that the classification loss explodes completely, L2 loss explodes, and we see that somehow it drops, but it drops to some crazy amounts anyway. So in this case, the learning became completely unstable. Okay, but this is a particular case of interacting with your training. Okay, another thing is getting insight into your data and what you're actually doing. So, okay, I have one anecdote prepared even. That Linus Torvalds said that he doesn't like debuggers in the Linux kernel. So he said he doesn't like them because if they perform some automatic action, that even if you are able to fix the problem or the bug, actually you get no insight into the problem. So he performs the debugging in the sense that you really have to manually find the problem. So that's not what I completely encouraged to always use some print statements and search for the bug in the code. But to have some more insight into the problem through, say, visual debugging, that's how we call it. So the bad practice is some limited monitoring of the job. The better practice is to get some more insight into the data, into what's going on in as much as possible. And the model jobs I've prepared to show you the case is one Bob's job. Oh, I moved. Where, it will be a little quiz actually. When we send the images from training and from validation, I'd like you to see how the maybe the validation first would be better. Let's see the validation images. And we have some probabilities, like I've previously said. Ursus is, who knows actually what Ursus is? Ursus is Latin for bear. That's how it was called, okay? So Ursus with 0.795 probability. I don't see any Ursus there, but that's fine. We have a bear here, that's great. Bison again, so we see that pretty much it's okay on validation, so it classifies well. But okay, that's not a bear, is it? Let's see. That's not a bear again. Okay, maybe there's some pattern here. I don't know. Maybe you see some pattern there. That's a bison, but with very low probability. Network's really unsure whether it's bison or bear again. And that's a bear again. Okay, definitely network's not perfect, right? We can see that network's not perfect from, say, classification loss, or we can see at the accuracy that it's not that high on validation. But, okay, not that high, it's still, okay, let's get the precise number. We see that it's about here, okay? But here we got some more insight into the data. So network's not perfect, and we're wondering why. And let's look at the training images, okay? At the training, we have bisons. That's great. It classifies bisons very well. That's a bear. That's precisely what it is. Oh, these were pictures in the data set, but it's like some noise we should delete probably. And let's get some, oh, that's interesting. That's a bear again. That's great, that is a bear. We keep just analyzing what's going on. Could go on and on. Oh, that actually is a bear. Okay, does anyone see any pattern here? Recurring pattern. Okay, it's not straightforward, so is it? Anybody? Come on, don't be shy. Yeah, they are really bad pictures. Like I said, probably some of them could be probably deleted. I made some augmentation. You see there's some slight rotation, but they are not that bad, I guess. If you see that in the training, the black and white pictures only in black and white are best, it's fine. And in the validation, we've got only bisons are black and white. So the network only from the visual, well, network is not that smart as we often think. It's deep learning network, that's great, it's deep network, but we may trick it somehow. And here we tricked it in the sense that in the training we have only bears in the black and white, and in the validation there are only bisons in black and white. And the network thinks it's a bear, okay, because this picture is black and white. Got it? It's clear. Other pictures are like normal, like RGB. So what we can do right now is like two things. We can either change our validation to simply better reflect our problem, but maybe it does reflect good our problem. Maybe soon we will get other pictures. Maybe we should add these pictures to train. We can just do something. But we can also do just augment our data, okay? So that's what Alice did. Alice did the data augmentation. Let's recall that Bob got accuracy, let's say 0.85. And Alice did some, I've called it with grayscale, where the training images are augmented. So both the bears and bisons are black and white. I think half of the bears and half of the bisons are black and white or whatever. And okay, first let's see that in training, this time it happens that we've got like Sometimes the bear is black and white. Okay, this one not sometimes the bison. Okay, so we've got black and white pictures, and we see that it really does increase our performance. So it's not like it's arbitrary. It really did work in this case. It's just like that. We see that. Okay. So insight into the data is something we really need during the exploration phase, during the training phase, if you want to upgrade our solution. That's necessary, absolutely necessary. Next thing is something we do all the time. So we hyper-tune our parameters. I guess in any model, from random forests till neural networks, there are like many parameters that vary, and we can do some optimization. And one technique is, well, what Bob actually did. Maybe I'll just show you. If you get back to the dashboard, you may see that Bob performed many experiments with different learning rates. Let's just see some of them. Okay, let's say 2 of them. And Bob started with a learning rate 0.01. We see that also in parameters, that he started with 0.01 instead of the standard, well, different learning rate. And he gets some results. In the case of the large learning rate, accuracy is not really that good. Okay, Bob performs many experiments. He tries to keep track of them all, but it's not a good use of the tool. So it's just a tool, and the way we use it is up to us, but it doesn't scale. In the case of learning rate, when you've got 5 experiments with different learning rates, that's fine. But it doesn't scale either with respect to the number of parameters, with respect to the size of the grid I'd like to apply, and so on and so on. So what we actually do, we perform grid search over the parameters, or Bayesian search, or whatever other optimization we'd like to apply. And that's actually what Alice did. She performed just the grid search with respect to the learning rate and got the result that the best job is with some small learning rate, I guess. Yeah. You can also see the particular result of Alice. She got, yeah, pretty good accuracy, actually. Okay. So you can run multiple experiments simply, use some, there are many optimization techniques. I guess there's even an open source algorithm I'll just mention for you to know with Bayesian search, which performs optimization over the parameters in the Bayesian way. Okay, it updates the posterior probability. So that's how you should do it. Yeah. And why I mentioned that? Because, okay, from some perspective, maybe it's not that precise. From some perspective, when you run experiments, say short experiments where you use random forest or whatever, maybe it's not that difficult. But in the sense of deep learning, where everything takes a lot of time, you really need to optimize everything. It's one of the things you don't want to think about. Next thing is, we again all know, it's like reviewing the history. So even though you got some result, like at some point when you say choose the best model, you really have to be sure that everything works. You don't want to choose the best model and try to, put that into the production, not being 100% sure that that's the model that you need. It's also the case of reproducibility of the model, but that would be in a moment, okay? Say we're still in the exploration phase, and we'd like to get more insight into what's going on. This time, what did Alice do and Bob? That's what Bob did, and it opens. Excuse me, I'll close some of them because I got lost. That's what Bob did. And does anyone see something strange about the experiment? What? Someone said it. Come on. Okay, it's obvious. Why it's obvious for you? Yeah, because you see it. It's straightforward. After you saw some experiments, you got used to what's going on, and it's quite straightforward that something's wrong, and probably you've also met such problem. What may be the cause of such high accuracy on both training and validation?
Overfitting?
Yeah, but you wouldn't overfit the validation that well if you train the model properly. Hmm? What leak? Precisely. If you got such a good result on validation, it's probably a leak, data leak. So what sort of leak did? Okay, how can we check that actually? If Bob didn't actually, okay, what could Bob do? We've all seen that Bob's really, trust me, we did. So Bob could, for example, take the Alice's code, which performed really well, change a few parameters, added something, and bam, we've got a new job. So how can we check Bob if there was no data leak? If we properly extracted some parameters into the job, we haven't modified the source code, because of course, if it's hard coded somewhere in the code, then we have to just, I don't know, use some version control and check. But if we abstracted the parameters, we just check what did he use, and bam, he is training validation for both he was training for both training and validation. He simply validated on train, and got the same curves. That's not good. Yeah, what did Alice do? Alice, well, it's straightforward. The good job of Alice is obviously didn't do this. Okay, it's train and valid. That's the way it should be. Actually, she gets worse results on validation, but that's fine. At least you can say that the result's reliable. And the second thing I'd like to encourage, highly encourage, is the teamwork. And by teamwork, I don't only mean that you should sit in one room and talk all the time. It doesn't make sense in many ways because it doesn't scale that well. When you've got 20 people in one room and they are trying to talk, it's more time on talking than on coding. It's not good. But also, it's even worse probably when they are working completely separately on the same problem, often doing the same thing twice. It also doesn't work that well. So good practice is transparency of the work. So when you should be able to, at any point of your work, look into the code of your friend and be able to know what he's doing and why he's doing it probably. Okay, so that's what I encourage. But okay, what's the common case when there's a teamwork? You have some limited resources. Say 10, 20 GPUs for computations. Okay, that's what we do. You compute on GPUs, standard deep learning case, and there's always a fight whether one project is more important or the other. Straightforward solutions like let's divide the resources over the different projects. It's one of the solutions. It has such drawbacks that some of the resources are often idle and the other team doesn't use them. So it's not somehow automatic. So you could use it, but if you have some notion of controlling the resources, probably automatic, that's best. In the similar way, there's a problem of environment where when one version, so say TensorFlow, doesn't work on CUDA 7.5 or 8.0, and you have to define properly the environments, integrate with some solutions like Dockers and so on. Okay, so you get the point. If you manage the environment with Dockers and have automatic resources, control of the resources, the workflow is more natural, and there is no fight in the team. Okay. Actually, that's also what Neptune solves. And there's a case of model reproducibility. In the end of the process, okay, say you've done everything right, you're the Alice of the world, and the natural problem occurs. Is Alice able to reproduce her model? So, yeah, that's with the help of the history, it's possible. With the help of the tracking of the code, Git integration, it's possible to reproduce everything from the environment with the Docker file, through the code with the Git, through the extracted parameters in the job, you're able to have precisely the same solution. And the manual process of reproduction, I don't know if you've met that, but something like trying to, a year has passed, the TensorFlow version has changed, the code evolved in many different directions, and then reproducing is really, really difficult. You don't want to do that. Even if you got that this network with these parameters was best, then putting that all into like one model again, it's something really, really difficult. And again, there's a phase of model deployment. So we are on this data science part where we develop the model. But in the end, you want to deploy the model. It's not like you're happy because you've done your job, right? And you throw it over the wall, and you hope the software developers will do their job and deploy it on some AWS instance with some RESTful API, and you're very happy that everything's okay. No, it just doesn't work. So some automatic deployment is great, like where you choose the resources, where you choose the environment, and with the proper DevOps practices, where there's some redundancy and high availability, you're able to deploy is one thing, but your client can really use it, right? Can really use your solution. Where when you worked for a year and the project is stuck on the phase where you can't deploy it and the end user can't use it, it's not a solution. So I'd like to tell you that Neptune can help your teams. So that's what you saw. That no matter what the technology you use, it's just a Python application you can import and it works. And it utilizes your resources in the sense I've described. You're able to have like an end-to-end solution to your data science workflow. It's already available in the sense you can just register to the Neptune. Thank you. So are there any questions? Yep.
I just wonder, how do you position this product with TensorFlow? For instance, you have similar dashboard over there.
I would rather say the dashboard looks similar, but the product is somehow different because it's more end-to-end in the sense you have GitHub integration, you keep track of your source code, for the parameters. TensorFlow doesn't allow that. Also, you have the control of the environment you run the project in, so it automatically schedules your experiments, for example, on the right environment.
So are you scheduling your tasks based on Kubernetes or?
On what?
On Kubernetes or?
No, it has, it's agnostic with respect to technology where you want to schedule the experiment. In the sense, Neptune allows you a mechanism for scheduling the experiments. Where you schedule them, whether it's through Kubernetes on AWS instance or whatever, it doesn't care. You're able simply to define a Docker file, and it's enough for Neptune, in a sense. It has all you need to reproduce the experiment and keep track of all the parameters. But it's somehow focused on this experimentation phase. It has this similar board as TensorFlow, plus all these integrations I've talked about.
One thing that I think is really beneficial, if not vital, for reproducibility of data science experiments is the ability to narrate your thought processes as you go along. To describe what your reasoning was behind the choice of parameters, etc. What sort of tools have you used to integrate? What sort of notebooks, for instance, have you used to integrate with your experiments here?
From what perspective? In the sense that do I start from a notebook and then run an experiment, or? Yeah.
Well, what do you use? I guess you'd have to use something in parallel. Is there something baked into this tool set?
I'll tell you what I do. Okay, yeah. How I perform the workflow, because that's very user specific. But what I do, I tag the experiments I simply like or think are somehow useful, important. So first you have like, it's divided with respect to the project and user, so it's straightforward. But then if I perform, say, experiment on RESTnet network, I just tag all the experiments with RESTnet. Then if I find some reasoning important, I tag that with another tag and so on. So through tagging, you can simulate pretty much everything. To me, it's quite natural. Of course, you can add some description. So then it's straightforward to keep track of it. Yeah, please.
Hi, can you tell us what type of time frames or stage of the project looks like theirs? So how much time you spend on the data preparation, how much time you spend on the modeling, QA, just so we get an idea of.
That's again very problem specific, because if you get the solution which is right very fast, then obviously you move to another phase. And by satisfactory, it's often either defined by the user, defined by the Kaggle competitors, defined by you when you perform your own projects. So I can't tell you when you are satisfied, really. But usually I can tell you the Kaggle because it's much easier because you have very precise timeframes, okay? So it's often like at the very beginning of a competition or actually also any project in this manner, you test reliable solutions. Reliable in the sense that they were either published or at least someone claims that the result is, say, good on GitHub or whatever. So if you know that, or you previously know that the solution should work. So first you test such solutions, and it takes, I would say, less than 1/4 of the total time. So you should do that pretty fast. Say a week, or it's quite straightforward. You just take the code, apply it to the solution, see if it works. So that's the first phase. But if it doesn't, if it fails in some sense, so in case of Kaggle competitors, it's straightforward because they can do the same. So you have to develop something more. But if it's a project for a client, sometimes it's enough. Sometimes you have to develop something more. Then there's this stage with high variance where you develop, say, new solutions in the sense that you have to experiment at least with the current state-of-the-art solutions and somehow explore them. And it might take another few weeks, I would say. Say in the time frame of Kaggle, which is 2 weeks, it pretty much ends on this part, because when you are somehow satisfied with the result, it's pretty much over. And then we have this development deployment stage, which is longer. Because there are issues with, experiment is usually a small part of the whole solution. In the end process, simply when you know the algorithm is pretty much not a lot of code, there are some libraries and so on, it works, you're happy. And that's what we've already done. But then there's a deployment stage, and then it really depends where you want to deploy it, with what API, what are the user requirements, how much more data your client wants to use. Because it might have been, in this experimental stage, you don't train on the whole data. Sometimes you do, if you are not happy with the accuracy, of course. But sometimes, if the experiment takes already 2 days, it simply doesn't make sense. You're running some estimates of your solution. So it really changes when you try to deploy the solution. And then it usually takes more. And estimates here, like I said, vary. It's months, I would say. Yeah. Sometimes also there's the issue, like I said, reproducibility. And again, if you have the right, that's really the case, that if you have the right tools to reproduce the solution, it's 1 day. If you don't have, you're adding, I don't know, maybe even it might take even longer than the previously exploration phase, trying to reproduce actually what someone previously done with some whatever. It might even take longer. Thank you. Anyone? Okay, thank you.